video today is going to be on the fundamental theorem of algebra. The fundamental theorem of algebra is if a polynomial of degree n, where n is greater than 0, then the equation has at least one root in the set of complex numbers includes both real and imaginary. Okay, so that sounds really complicated. It's really not that bad. How many solutions or zeros should you expect to find on an equation? So this is why we use the fundamental theorem of algebra. We look at the degree. So when we look at our polynomial equation, we look at the degree. The degree tells you how many solutions an equation is going to have. So given each polynomial, we're going to solve. And we're going to solve using Unit 2 methods. We have quadratics. These are all quadratics. Actually, I'm going to factor. Difference of two squares, x plus 4, x minus 4. That tells me x is equal to a negative 4. That tells me x is going to be equal to a positive 4. And I knew I should have two solutions because I have a degree 2 polynomial. And in this case, I have two real solutions. So the degree tells us how many we should expect to find, and it can be a combination of real and imaginary. If I look at our next one, we multiply to the outside, add to the middle. That's 5 and 5. That means that we have x plus 5 quantity squared. That means I have x is equal to a negative 1. Now this is kind of strange. We should have two solutions and we only have one solution. Okay, so we're going to backtrack a little bit. If you remember when we learned about the discriminant, there was two real, two imaginary, or one real. We're going to kind of disprove the fact that we said it was one real. We weren't very specific when we said one real, and we hadn't learned about this yet. So we do have two real solutions here, but only one unique solution. So when we did the discriminant, we should have done two real, one unique solution, and then two imaginary. When we have this x plus 5 quantity squared, this is going to count as a double root. So it counts twice. It's a repeated solution. So we just have to be careful and remember that this happens when the vertex is on x-axis, or that's where your intersection point is. You only have that one intersection point. So this is the one that can kind of throw us off a little bit. It is two real, it's just one unique number. So don't fool yourselves, because we're going to use that degree to really check our work to make sure that we found all of our solutions. Don't forget, this is a double root. It counts twice. One unique number. Okay, number 3, we can't factor. There's no two numbers that multiply to 5 and add to 3. So when that happens, we've got quadratic formula, we've got completing the square. I don't know about you, but I'm going to use quadratic formula. So the opposite of b plus or minus the square root of b squared minus 4 times 1 times 5, that AC, all over 2 times a. We simplify the discriminant underneath that square root, negative 3 plus or minus the square root, the negative 11, all over 2. That means it's a negative 3 plus or minus I root 11 over 2. Here, again, the degree was 2. We have two imaginary solutions because of that negative underneath the radical. So all of these had two solutions. They can be real, they can be imaginary. How do you know how many solutions are real and how many are imaginary? Real solutions our x-intercepts, imaginary, whatever's left over. Imaginary are the remaining. Now we said x-intercepts, that's because what we're going to do is we're going to move everything over to 0. Otherwise, we know that we're just looking for those intersection points. Okay, so graph the polynomial, then determine how many and what type of solutions we have here. Bust out those calculators. We have y equals, we have x to the 5th, make sure that you arrow to the right, plus 8x squared minus 7. All right, so before I hit the graph button, I'm looking at, I have x to the 5th, x squared minus 7. This tells me that I'm going to have 5 possible or total solutions. Remember, the degree tells you how many you're going to have in all. I go to zoom 6. Hopefully I can see everything, and I can. All right, so I'm going to sketch that graph here. Now I know that I'm going to have 5 total. When I look here, I have 1, 2, 3 real solutions because I have 3 x-intercepts. Now if I have 5 total, 3 real, that means that there are 2 left over, so there are 2 imaginary solutions. This is the fundamental theorem of algebra. The degree tells us our total, and then we can figure out real and imaginary by the x-intercepts. Remember, we can't use graphing to find the actual imaginary solutions. That's why it's what's left over. All right, if I go to number 2, we've got 9x squared plus 3x minus x to the 4th plus 10. Don't get fooled. Remember, it's not just the first term. You have to look. This one, unfortunately, was not in standard form for us. Our degree is 4. That means that I have 4 total solutions. We go to our calculator, y equals, clear that out, 9x squared plus 3x minus x to the 4th, arrow out, plus 10. All right, I gotta change my window here. So I can see this, I can kind of start seeing this right here, so I'm gonna move my window up. So I gotta change that y max. I'm just gonna change it to 40. I hope that's enough. Yeah, okay. So I can see my graph here. We sketch it. And when I look at our graph, we have 1, 2 x-intercepts, so we have 2 real. And the leftovers, if there's 4 total, 2 of them are real, that means that there are 2 left over that are going to be imaginary. Imaginary always have pairs. So I can't have 1 imaginary or 3 imaginary. So if you end up with an odd number, most likely you forgot about the double root counting as 2. Okay, that is all for the fundamental theorem of algebra.